I'm Jordi Baylina. I'm the technical lead of the Polygon zkEVM right now. But in this context, I also am the creator of Circom, of Snark.js, in the zk context. I mean, pure language. Web hacking, writing smart contracts, auditing. Mainly a developer in Ethereum since 2015, just trying to make this to happen. By the way, privacy is a value that is a requirement. I mean, it's a core value. I know that in the last times it's something that we put aside. The last incidents of Tornado Cash and so on probably even lowered the needs. But it's very disappointing to see that that we are not giving too much importance to privacy. But privacy is fundamental if we want this technology to be mainstream. Just to be clear, I mean, and just think about, imagine that your bank statements are public. I think that nobody wants that. Okay? So you need privacy. So work needs privacy. Work is not privacy, it's a need for privacy. So do not be afraid about talking about privacy. Privacy is a good thing, it's a necessary thing, it's a neat thing. I would say it's even a human right. And if we don't build systems that are private, systems are not going to succeed.
I totally agree, and I think also that maybe private and compliant too. I mean, we can
privacy
achieve both.
Privacy is not a synonym of
doing bad things.
Doing bad things. I mean, it's like if you need privacy, that means that you are doing something wrong. I mean, this mindset is absolutely wrong. It's very inside the people, but that's not wrong. I mean, privacy is like freedom, and the problem of privacy is that if in general, most of the people don't need privacy in every day, in the same way that they don't need freedom because they are somehow free. But the moment that you need it for some reason, if you have not been working on privacy before, then is when you realize that
that something is missing.
That something is missing. And again, please do not confuse privacy in doing something wrong.
Yeah, do you want to introduce yourself?
Maybe we can introduce ourselves. Yeah.
Okay.
I am José Luis Muñoz. I am an associate professor at the Universitat Politècnica of Catalonia. I am also the director of a master in blockchain technologies, in which we have a big subject in cryptography and in particular in zero knowledge techniques, because they are very, very related with the blockchain. The blockchain, I would say, is the perfect scenario for all these techniques. Either for privacy or also for scalability. And from some years, I also collaborate actively with the Polygon team, with Jordi, because we know each other from some time ago. So I would say that this is my profile. By the way, Jordi said a lot of things, but he's also the co-director of the master. So. And now here we have Marta.
You probably know them, you don't know me. I work at Dusk, and actually I think that since Jordi already brought the topic on the table, Dusk is a blockchain that is intended for the financial market. So in there, privacy is not just something nice to have, but it's actually a requirement, like the example Jordi put. When you have transactions, you don't want your data to be out, so that's something that we need. So we are working on that field, but also we need to be compliant with the law. So there's some trickiness, and I think the question that one of you, that you mentioned before, that you had on, okay, what should we do? Like if we have something completely anonymous, or should we, in our case, we need to be compliant with the law. So there are like some problems that we need to still figure out, and we see how the legislation is also changing. So adapting to that is also not an easy task. So indeed, it makes a lot of sense to bring this topic into the table and have some conversation about it. Yeah.
Cool. The idea here is, well, I don't know if you want to.
It's okay.
Go ahead. I mean.
No, go.
Well, I prepare like some guides to follow some line, but we can go out of this line without any problem. My idea was to start talking about zero-knowledge technologies, I mean, how they evolved, which are the main paradigms, and maybe what we're doing now, okay? So maybe it's a little bit technical, and the thing is that if you want to make any question during our explanation, it's perfectly fine, I mean, as Brando said, okay? So maybe start with this, or you wanted to say something? Okay. So yeah, let's talk a little bit about the evolution of the zero knowledge. I mean, at the beginning, zero knowledge started back into the 80s, so it has many years. And the thing is that there were techniques to prove very specific things, like, I don't know, I know the discrete logarithm of this number, okay? Or I know, I mean, these two cryptograms contain numbers that if you add them, then it yields this other cryptogram, for example, something like that, okay? And then composing or proving complex stuff, it was really challenging because you had to mix a lot of different techniques, and I mean, it was a task only for cryptographers, I would say.
Yeah, at that time I don't know how many people here, they heard about the cave paradigm, I mean, the cave problem of the zero knowledge, that, I mean, a gun entering in a key and opening the door.
Yeah.
I mean, you read that and you don't get it. I mean, or it's very difficult to. You can get it if you know what zero knowledge, and then you go back and then say, okay, that makes sense. But if you read that for the first time, I mean, that's a very theoretical thing. You're not going to build privacy
from this.
Okay? But that's where the starting point. So
it's very good to explain a lot of things in cryptography. In fact, I use it to explain many properties.
I'm not saying that that's not a good example, but it's
not practical.
Not a practical one.
Way but that's the 80s, so where we started. I mean, you can jump directly. I would say that the first, there are some, I mean, specific applications, but probably the first high-scale real application in the space, I mean, in the crypto space, and that actually, I would say that's the application that brings zero knowledge to mainstream in the, at least in the community sense, and in beyond the academic environment, was the Zcash, the Zcash chain. Actually, there is, I would say that most of the people that we are in the ZK world in the space, we come from there. I mean, that's the original point, the Pinocchio paper, and then later Growth 16, and I mean, that was I would say that was the
big thing in the industry started there.
But I think it comes very much from what you said, at the beginning you only could prove few things, and then the examples were very toy examples, like, okay, I get the idea of zero knowledge, but what can I do with it? And I think that when there was like an efficient proof system that you could use to prove very general statements, this is where like Zcash could really come in, because you could prove that any computation was correct. So it's like, okay, all the computations, all the checks that the network does, now it can be done inside the zero knowledge proof.
There may be a special mention here to the bulletproofs and the Bitcoin community. They were already working, some part of the Bitcoin community, they were already working in some bulletproof privacy by the time and so on. But the ZK, as I mean, the general purpose ZK, as we understand it now, everything comes from there.
Yeah.
Here is I mean, if you see Adrià already explained it a little bit, the letters, okay? But there is one part, is the non-interactive part, that this is the Fiat Shamir. I mean, the idea is that, so before Fiat Shamir, the proof where I want to prove something to him, okay? And then there was a dialogue between him and you send me one number, and then you send a number back. I mean, it was an interactive protocol, okay? Fiat Shamir, what does is, okay, so I don't need to prove to you. I can prove to the world, because with a single message, I just can't prove to you. But if I can prove to you with a single message, I can send this message to the world. Okay, so this is the non-interactive. This is what makes this public, and this is, I would say that this is another important step that
NISIX,
that
non-interactive zero knowledge.
And I mean, the Fiyesham heuristics actually what allows you is to convert any or almost any non-interactive. I'm not mathematically correct here, but so let's say any interactive protocol and convert it to non-interactive somehow. This is also, I mean, it's a very simple paper. I mean, very intuitive, I would say. I mean, it's not simple mathematically.
No. Well, no, I just wanted to say that I think the idea is simple, but we've seen like some recent papers where there are attacks, so I think it's very subtle as well. And sometimes the implementation of Fiyesham can be a bit tricky. But this is like in general in cryptography, I think that...
In cryptography, when you repeat things, you need to make sure that, I mean, that one step is okay. It doesn't mean that when you repeat it is okay, because there you may be introducing some, you're decreasing the probability probably of the soundness of the system. So there are a lot of, recent papers about how this is done.
Yes, still, like it's amazing that they had this idea. Yeah, indeed.
There is a rule. I mean, when they started doing cryptography, I mean, just much before blockchains, there was a rule that I think it's a still valid rule. And is if you are an engineer and you are not a do not invent cryptography. I mean, this is something that you're gonna mess up. So doing cryptography for yourself is never a good idea.
But we do it anyway.
But actually, this is what we are doing. So this is very, very, very scary. And I mean, that's why. I mean, and this is what's about the programmable cryptography, and this is the era that we are right now. I mean, the zero knowledge, and this maybe the next step is that the moment that it's not that you need to prove something specific, that you can prove anything. I mean, you can write a circuit. You can write, when we say a circuit is a program, and you can prove that the computation of that program is correct. Okay, and this program can be anything. I mean, actually, is
any deterministic computation.
Any deterministic computation. Okay, so here we are programming cryptography somehow, and here we are inventing a lot. And here it is important, for example, that all the teams that are doing this, they are mixed teams between engineers and cryptographers. I mean, even if you're an engineer and you're doing some crazy things, having cryptographers around just to double check what you're doing, I would say is fundamental, is a must. And I mean, here, Marta at some point, Hector, I don't know if he's here, but I mean, at least in our team, the role of the cryptographers, it's not on your team. I mean, I would say in all the teams is crucial and fundamental because I mean we are playing around, playing probably too much with maths.
Still, I think maybe from the academics there's a little criticism of inventing, but at the same time I think that the engineers and developers they've pushed a lot. So to really build things. Okay, there might be some errors, but at the same time they are also pushing for the others, for cryptographers to go and fix things. But at least there is something done, you know. So I think, I agree with you. But at the same time, I admire like this capability of building, you know. So definitely
I would say also the paradigm now of zero knowledge systems is much better for creating because you have new languages to express what you want to prove in a much easier way and with much less knowledge of the, insights of what is going on, mainly on. And now we have this separation that maybe we can talk later or now about the front ends and the back ends, and this is helping quite a lot the development.
Well, in 2016, 2017, where the people in the community start to understand this technology and they knew how it works, is then when the first toolings for writing these circuits and proving these circuits starts to appear here. Of course, Circom and SnarkJS is the one that I read, but there was others.
Very great computation.
SnarkJS, and later on there was Noir. It's also there. I mean, there is a lot of tooling libraries, IRQ. I mean, there is very different toolings, different library sets, different ways of writing zero knowledge. So the zero knowledge technology was, I would say, available to engineers. I mean, it was not something that you need to do something strange in a protocol, in a black box. with crazy math inside. I mean, it's like, okay, here is, okay, there is some crazy math, but it's like somehow encapsulated, and you can just focus in writing your program, in writing your application, and you can use it. And here, I mean,
you have an easy language for it. I mean,
yeah.
a language for you that
it's a very low. In the case of Circom, for example, it's a very low-level language. I mean, it's a language that I would say you need. It's good that you understand the essentials of what's going on behind, but allows you to, I mean, to create complex things. I mean, you have
still it's easy to forget some, you know, to put some equation there that makes the system.
Yeah, currently probably Circom. I mean, I don't have statistics, and this statement may be wrong, but probably if it's not the most used language, probably it's one of the most used languages.
Sure.
In there, it's easy. So it's like, okay, you can write a game. I mean, you can write a proof of privacy of voting system, or I mean, whatever zk or even a rollup with Circle, and yeah, you have a zero knowledge. And this has been probably the best tool you had till now for creating zero knowledge.
Yeah, I think something that you did really, really great with Circom is that you really decoupled the writing the circuit versus the proving system. So this is completely modular. So even if the proving system changes, you can still use the circuits that you built. So I think, like, I don't know how you came up with this idea, but I think there was nothing in the space at the time. So the fact that you could see, like, building all this framework and really decouple the different parts, I think it was
well. Here the difficulty
nice.
of that. The difficulty of that is that. So it's not, I mean, for the constraints, when you have the constraints, it's quite easy to put the constraints in a JSON file and okay, and move it to that. But the problem is how you pass, I mean, the witness computation. I mean, the problem is the circuit needs the witness computation. So how you send a witness computation to the front end, to the one that's building the proof, because building the witness, it's very specific to the circuit, but at the same time it's needed for generating the proof. So Circom what actually did was, okay, actually
make this automatic.
Yeah, make this automatic. But this is probably the difficult part of the most difficult part of Circom on this split.
Was it also, like, for you the most difficult part to implement, or?
Well, yes, because at the end is. Well, it's probably yeah, because it's generating code. I mean, it's the real compiler part. The other is interpreter, but this is writing code. In this case, we generate just C code or WASM code, and this was enough for most things. By the way, we are evolving that part of Circom in next versions. But
they make it more efficient, or?
Well, the idea is that what we are doing. I mean, what we are start planning to do is. Having a kind of so instead of writing to C or writing to WASM, the idea is to write like our own specific virtual machine, so that you can have this interpreter of this virtual machine in any language. And this virtual machine is very specific, so that it can go really easily and really fast.
Yeah.
The biggest difficulty is that this virtual machine needs to be parallelizable, because writing the witness computation, if you want to be efficient, you need to parallelize. So it's not just writing a virtual machine, you need to write a virtual machine that's actually written in parallel, and this is where the difficulties come from. But this is what we are already started working on, and I think this would be good, because then you can plug this witness computation in Rust, you can plug it in Java, in C++, so in any language, and you don't need to write a specific model for each language. Also, the other important part of that is that variable circuits. I mean, the problem of that is, imagine that you want to. I mean, if you are working always with the same circuit, you can embed this code into your program, and that's it. But if you want to have an application that's able to prove many circuits, so the circuit it becomes like a variable, then how you you need to send kind of a compiled program. Okay? For example, you want to do that in a mobile phone, and this is not allowed. I mean, iPhone does not allow you to send a program and execute the program on that, and even and that even can have some security concerns. So writing this specific virtual machine with big prime fields, parallel, so on, this makes a lot of sense, and this is one of the
Evolutions.
Next
that
steps.
we are working on that. This is the first time that I'm talking about that. But yeah, we are working on that.
Okay, nice.
Cool. We have advanced quite a lot in many topics here, but essentially we're talking that this is one of the models of, this is one of the ways in which we can model the proof that we're going to build, that is building circuits. Okay, and in these circuits you will have like things. A circuit is a circuit, so it means it has like wires or signals, and then we do operations there, like additions and multiplications, essentially because we always work in an arithmetic structure that is called a field, and then in the field you can do these two operations. And from in this circuit we have like values that are private, that the computation will be correct. The thing is that I know some inputs here that I put, and they will never be shown, but the output is correct according to these inputs that I will never reveal. So this is the privacy part. And then in the circuit we may also have like public. We always need something public because we need to check some proof. So typically the outputs are public. And then we have a lot of values that are related with the specific circuit. How the circuit is connected and which values it is using they are specific of the computation that we are doing. So we have these three types of values here: fixed, publics, and witness. And this is how we do proofs.
Yeah, one interesting topic here is that we are talking a lot of times about circuits, okay? And it's important to understand that where it comes from. Because circuits sometimes can be called a deterministic program. At the end, it's a program that want to prove that the execution is correct. But why we call it circuits? Because we call it circuits because we think in the hardware model. And the circuit is you have gates, you have two signals, and maybe you have an AND gate, or if it's an arithmetic, not an addition, because you have two signals, you add, and then you have another signal, that's an addition. You have two signals, you have a multiplication gate, and you have a multiplication. And then the circuit is just, you have inputs, and then you do additions, multiplications, and you come up with some outputs. Or that is a deterministic program, but we call it a circuit because we build it this way. And it's interesting to think that this hardware model, when we are building a circuit, we are building a circuit with ANDs and ORs, but you need to think that there is no clock. It's electronic without clock. You put inputs, and then you have some AND ORs, and you always goes forward. Okay, you have a lot of gates, and then at the end you have an output. Okay? So this is how circuits are built very much in hardware and in Circle, very much. There are some tricks there, but that's very much how you are building the circuits. And you can see here the limitation that it has. If you want to do a complex computation, you need to, imagine that you want to build something similar to a processor. A processor is different steps, but if you want to build it as a circuit, you need to put the full processor, okay, for the first instruction, and then you need to repeat again all the gates of the processor. It's like you're putting like many processors one after the other because you don't have a clock. Everything goes forward, okay? And this is what makes complex things impossible. A circuit, so all the zero knowledge they are limited by the number of constraints, number of gates, the number of things you can do. A lot of times are limitations on the same prime fields, aduacity, and you have this limitation, and it's limited. Maybe there can be hundreds of millions, but it's hundreds of millions. It's not hundreds of billions. Okay, so you have some limits, and at this point, writing something that's similar to a processor was
This is like the other approach to build zero knowledge proofs. We have like this circuit with any type of connection, and then we have this other approach which are like more state machines, or some authors they like to call it like a structured circuits, because there is like this sense of the computation is progressing, and we are proving relationship between rows in a matrix, essentially.
When you are doing the same thing many times, and this is the idea of a processor. I mean, the processor is, okay, you are repeating. Or serious if you want the idea of a clock, okay, so it's like, okay, you have something, and then you repeat again, and then you repeat again, and you repeat, but you are doing something. Actually, the constraints are the same constraints that are repeated many times, okay, so here is where the idea of heirs, the Starks, and this idea of even the polynomials, but I mean, constraints that are, it's the same constraint that just repeated many times, and then you can work not with signals, but you work with a polynomial. If you want a polynomial as an array of signals, I mean, a polynomial can be understood as an array of signals, and then you apply the same constraint, but not to a signal, to a polynomial. So actually, you are doing million of checks per constraint. Okay, and this is the main evolution of these new ways. I mean, we are talking here. Well, Starks are older than that, but I mean, this is all the zkEVMs and all the modern zk circuits are based very much on this model in the sense that we are repeating.
And then the idea here is very interesting because, I mean, one option to prove something is to write the circuit, but I mean, it's much better than trying to, mix specific cryptographic techniques, but still is quite low level. So in this new way, we can build, if we define our computations with this other model, like a state machine, then there we can create also instructions and then prove these instructions. And then from the point of view of the developer of the application, you are like a little bit it's more abstract, and you are like in a layer above, and you only need to write the thing that you want to prove as a set of instructions that then with this model they are built in this matrix, and finally it's proved. So we are a little bit more far from the low level, which makes building the application easier for the privacy developer in this case.
But here is this is very much, for example, what the Polygon zkEVM, I would say that's the biggest contribution we made, is that we created somehow the first zk, or at least the first practical zk processor. I mean, it was a processor that actually in this case emulates the EVM, okay, but it was technically it was a processor. I mean, it was a processor with instructions, with memory, with ROM running on this processor, with some coprocessors around.
This allowed also to parallelize the development of the system, because we can have people devoted to the proving this state machine, and then other people writing the programs that we finally want to prove. In your case, there's
exactly. But that means that writing circuits, instead of writing like the circuit of the electronics and putting the components and code together, it becomes more similar to writing a program. Of course, it's somebody just write the processor, and then there was another team that was just writing the program running on
top of this,
on that processor. Okay, so this changes a lot the paradigm of writing zk circuits, because at this point of writing a zk circuits, you need to just stick to a processor. Actually, I mean, the new tendency, and this is where everything is going on, is, so okay, what happened if this processor can be a zk processor, I mean, a new processor with new instructions, with new assembly, and maybe optimized for zk. Or you can say, okay, why don't you emulate a standard processor? Why don't you emulate a RISC-V or a MIPS or some other processor? Okay, and this is, for example, projects like RISC-0, SP1, I mean, or Polder. I mean, they are doing. I mean, they just built a processor that's just a RISC-V, for example, and then that means that you don't even need to write special assembly. I mean, you already have an assembly, you have a full stack on that, and then you can just write the Rust code, compile to RISC-V, and then just execute on those processors.
I would say this is one of the main things that is right now happening on the.
This is what's happening. This is what's happening right now. I mean, projects like RISC-0, like SP1. I mean, those, and we will, and many other. I mean, we will see. Yeah, there is many others, and this is where I would say the engineering force is working on that.
By the way, here in the public we have Edu that he did a really good state of the art about this. So you can also, if you have questions about this, you can ask him.
What I can say on this, and this is important, is first that here is of course the debate if it needs to be a RISC-V or a specific zk processor. If you are doing a specific zk processor, it's going to be more efficient than RISC-V. The problem is that the development time. I mean, you need to have a special assembly and even the auditing of it is much more, so it's much slower time. So it's like, and here is, that's compensated. I mean, the thing is how much slower this is going to be. It's going to be 5x slower, 1x slower. Is this 5x slower enough for this application? Not. Well, this is what we need to see. But what's clear is that I mean, at least the development time is going to be much faster if you already reuse something like RISC-V. Okay? And here, of course, is the efficiency that this happens. Talking about efficiency on these systems, we need to see how efficient all these simulations can be built, and there's still some margin to improve here, so we need to see what it gets. Here is important also to see, I mean, you see, one thing that's going to become very, very important in the next, the next years is that if you are trying to build everything in this processor, I tell you that's not going to be efficient. I mean, if you are trying to do a catch-up inside this processor, this is going to be very, 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 very slow. So here it's going to be very important what we call it the coprocessors or the precompiled. I mean, whatever these, and this is also like other processors of other hardware, other hardware around that somehow helps or is doing things, specific functions that are used many times, that they are very concrete, and they are, I mean, and they can be put in parallel. Okay, and this is going to be important here. For example, catch-ups, hash functions, even of course arithmetic, big arithmetic operations.
Essentially, you have like a specific structures.
Specific structures for
building,
specific functions, depending what your application, what you are building. This is going to be fundamental for being efficient. Okay, on that, because if not, it's going to be, well, we need to see, because sometimes it's, even if it's less efficient, maybe it's enough for the application. And this is the other thing that's very we need to see. I would say it's a market decision. It's like, I mean, it's 5 times slower, but I mean, it's okay. I mean, I'm going to the market faster. I can audit much better. So the advantages that I get are much more than that. Okay, this is what we will see. But if you are not going this, I think that the gap is going to be too much. And the other important piece, I don't know if you mentioned in your the other important piece here that's going to be fundamental is the hardware specific. I mean, building these proofs in hardware. I mean, there is some currently there are some important projects that are building hardware specific ASICs and
yeah, to make, I mean, all the operations that we are doing, they are working on a field. And yeah, I would like also to talk about a little bit some, inner things of how we prove. When we prove, we need to build essentially, when we prove with this state machine model, let's say, or with this matrix model, we need to build matrices, and then there are relationships between cells in these matrices. And these relationships are essentially what define operations also. And here we have to do a lot of operations with fields. At the beginning, we just start doing cryptography with the circuit-based approaches, which were using very big fields, like 256 bits, something like around these numbers. But then here we realize that many times we are not using, I mean, we have a lot of, we have cells in these matrices, and we are just using 0 or 1, and we have there a capability of using 256. So we are wasting a lot of resources here, which translates into slower operations, bigger memory, and so on. So now the trend is to try to use smaller and smaller fields. Okay, so in fact, Polygon, the first version of the zkEVM was in a very big field, and then it was reduced to a prime number which is less than 64 bits, which is a Goldilocks-like prime. It's not exactly Goldilocks, but, and now hardware is there is a company, right? I think it's Fabric, writing processors to do the arithmetic in this field specifically. So people building hardware, they are also taking a look at this market, and they are building processors, hardware processors, to just prove these things. And now the trend is even go further, which is doing fields even smaller. Okay, so for example, one of the teams in Polygon, Zero, is just building a smaller, building the EVM, it's a Ethereum EVM, but in an even smaller field, which is the Mersenne 31, which is below 32 bits, and this has many nice properties because you can accelerate these operations in GPUs. For example, we use CPUs of only 32 bits, and so on. So this is one approach. So there is people just trying to do smaller fields, and then there is another approach which is doing it even. Which the smallest possible field, which is just a binary field, which zeros and ones. And then when we need to do operations, this such a small field is also challenging because we didn't talk too much about how the system works, but at some point you have like a lot of values and you have to do interpolations and build polynomials, and then we check that everything matches using these polynomials and not a lot of equations. Okay, this is the main idea of how these systems are made succinct. So we have to interpolate here, and then for this we need to use efficient algorithms. The most efficient one is the NTT, the number theoretic transform. And if you are using a binary field, this is challenging because to apply this algorithm, you need that the field has some specific form that has a big power of 2 inside the groups of this field, and doing this in a binary, you have to adapt a lot of things, but this is a path that just started, and try to do all these operations in binary fields.
But we see, we start talking a little bit about the future.
It's the future, yeah.
Sorry, I just had a question, or maybe to make sure I get it right. So, for example, in circuits, the type of protocols that we apply, they rely on certain assumptions. So those assumptions require primes to be very large. So the fields were very large because of this, because otherwise it wouldn't be secure. So I think that the type of protocols that you apply on this other computation model, they rely on different assumptions. So this is why they...
No, we still need big
you can use extensions, for example, or just repeating...
But not for the discrete logarithm. So
you start building all your computation with a small field,
and then from there you translate it.
When you need to give the security there, and you need some randomness. The randomness comes from an extended field, which is a much bigger space.
Okay, because as I understood it, like when you apply the technology of Starks, I thought it was like more of coding theory and all of that. So this is why they could.
At some point you need the cryptographic part, and then is when you need to work with extensions.
And then,
this is like the last.
Okay.
The last moment.
It saves you memory because you are doing stuff with small numbers, and then when you need to prove something, generally there you need a big number as random, and there you use an extended field. Mm-hmm.
But in any case,
this is a little bit technical. I don't know if
talking about the future here, I would say that there is some margin of improvements in small prime fields, in GKR, in the Starks, in some techniques for arithmetization. This I would say that, but I think that this is quite limited. You never know because, maybe there is some innovation that happens, but I don't think that here there is a lot of margin to improve. let's say maybe here is an order of magnitude, but I don't think that there is much more than one order of magnitude improvement in applying these new specific things. And the real improvement will come from the hardware acceleration. And here is where hardware acceleration, GPUs and even hardware acceleration, this will be, here we can expect 1 to 2 orders of magnitude more easily with a specific hardware on that. And the sacrifice somehow and okay, this increase on the technology will, what's going to be imposed is this standardization. This standardization of the processors. So it's going to be some. So it's not. What's clear is, I don't know if it's going to be a RISC-V or it's going to be a zk processor. But if it's a zk processor, it's going to be some standard zk processor. So with
some standard field, and finally,
with some standard register. It's going to be full stack. You will be able. So the same way that you have RISC-V, Intel, Motorola, or whatever processor, you will have another processor that's a zk processor. That are the 2 options, but probably what looks faster, because you don't need to implement all this stack, is RISC-V, and this probably is going to be in the beginning, but maybe for, at some point, for optimization of things, maybe it makes sense to have a zk processor with a full stack built on that. This is the 2 options, but what's clear is that the zk processors are going to be written in Rust and in C++ or in any high-level language and compiled to a zk processor. It's clear that in the short term, these coprocessors are going to be fundamental and important. So I don't think that in the short term, a single processor is efficient enough to build applications. So they will require these coprocessors then. But this will simplify, and then auditing and all the auditing process, all the creation process, all the development process is going to be accelerated a lot. And when you are putting all these evolutions that are happening together, this is where we will enter to this new era of the zk snarks.
Yeah, I have a question for the panel. So I see very marginal effort on doing like formal verification on these new zkEVMs. So at some point I find it like I'm worried because when you are executing everything in some servers and the same code, there's no duplication like in Ethereum, that you are running different different kind of implementations. Is there a way to avoid problems? But when we have only one, it might make sense to be sure that this is exactly what you want to execute. But I don't see a lot of people that it's interested, but I don't know if there's enough effort on this.
I would say that we are still we are starting to be in the process of standardization. And what I'm saying standardization is, at some point, so right now everybody has each company that's building something like that has their own processor, okay, and their own zk, their own thing, okay? But at some point it's going to be some standard processors and maybe some standard coprocessors, and the people will just put them together, okay? So at this standardization and formal verification is going to be easier because the number of pieces that you will have to somehow audit or formally verify are going to be less. The second part is this modularization. When you have the different coprocessors, you can formally verify maybe one coprocessor, maybe one arithmetic coprocessor. There are, in the case of the Polygon zkEVM, we have some pieces that are formally verified. But they are complete. It's not the full system. It's just the arithmetic state machine. We have some proofs that this is, but just the arithmetic. Okay, so, but with these coprocessors, you will see that of these pieces, many of them are going to be formally verified and so on. Some of them are going to take longer, but they are more instructed there. But this, I would say, the way to go is less pieces, I mean more standard pieces, so the total number of pieces is going to be the number of pieces that's used in the world. It's going to be handset of pieces, and they are reused for all the projects, and the formal verification, and even the auditing and all the securitization of that will be modular. I mean, will be modular based. I mean, just okay. So it's going to be some modification on that, modification on that. This is where, I mean, this is the tendency, again, it's the future, you have a crystal ball, we're talking here about the future, but this is where I see that the tendency is going. I don't know, Edu, what you think about that.
I agree. I think once you have a single piece that can be reused in many applications, it pays off to do this expensive part of auditing, especially formal verification. Maybe previously, since we build one thing and 6 months later it's outdated,
Yeah.
it doesn't pay off. Very true. Yeah. But I also think, I remember Risk Zero was also making a big effort on formal verification.
They have one guy that is starting to work on this.
Okay.
That is super expert with the like the KVM and with like things like that.
You need to start with smaller pieces, and from there just keep going.
Yeah, maybe we can open up for questions, right?
I want to introduce two more topics very quickly, just to to mention the umbrella of things that are being done on the zero knowledge space. Another topic right now, hot topic, let's say, or I don't know if it's hot, maybe it's starting to be more warm. And here we have Jean also, which explained it a little bit. It's about lookups, because we have these different matrices, and then one matrix is computing one thing, and we are using the result of in this matrix. We want to use it in another matrix, which is probably the main loop of execution, and then we have to do a lot of. This is one thing that happens, that for the reason that we need to do these lookups, which means that we are checking that one row in one matrix is the same as another row in another matrix. This is one option. One of the things why this lookup technology is being used, and it consumes quite a lot of resources in the prover. So there's many research on this topic. The other reason is because it is much easier to arithmetize something if you just build it is easier to say, to build a table and say, okay, the operation that I want to do, I describe it as a table, and then I check that the operation that I'm doing is in this table. And this model is being pushed to the maximum with new state machines that just don't provide, that just arithmetize everything with just tables, okay? And this is like the lookup singularity, I think is called, or Barry called it like in this way. So this is another research area. I don't know if you...
Yeah, well, here I want to comment there is like the two, I would say the two tendencies, or two schools. Two ways of writing this structure.
Arithmetization of
processor. One is, let's call it the Halo-2 way, okay, which is I would say is theoric, and the other, let's say, is the Stark, the Stark way. Okay, and let me explain you the two, because both of them, is not that there is one that's better than the other, it's just different. The Halo-2 is like, okay, the Halo-2 is very optimal. It's like to try to reduce the number of cells, it's trying to reduce the number of polynomials, and the idea is that they're putting gates, they're trying to reuse all the pieces, okay? So you have a set of cells, and you are putting gates in a very, let's say, unstructured way. You are recycling these polynomials and putting maybe one gate here, one gate there, and then just trying to build this way, okay? The other technique is, and then here, you have the advantage that you have less cells in general, because you are recycling of them. Of course, you have like the arithmetic, the complexity of the arithmetic is much bigger, okay? And the problem of that is, for example, in the Windows computation and so on, it's very difficult, for example, to parallelize because it's very unstructured. I mean, it's very random in that way. Okay?
This is the scroll approach, maybe, or it
It's-
was.
I don't know what's scroll doing. I think that they are. I mean, I think that here is interesting because I don't want to mention projects names, but
Okay.
but some of the projects that started in Halo 2 somehow they move to the Stark's way, but the people that's in the Star way is somehow also moving to the Halo 2 because they are trying. Each one is trying to get the best thing. So and then probably the equilibrium is something in the middle somehow. Okay, but the other structure is okay. Let's not mix the things. Let's put one machine for each thing. Okay, and then you have one machine that's just doing arithmetic operations, another machine that's just doing catch-up. So that means that you end up like having many polynomials, and a lot of times these polynomials are not even used because so from the theory perspective, I mean, you have much more cells, so theoretically the performance is worse. But because the system is more sorted, I mean, it's more Cartesian, I mean, you can parallelize much better and you can optimize this much better and you can go much faster on that. So at the end,
not clear, which is.
It's not clear. So
there are a lot of trade-offs here. Yeah.
here is interesting. I mean, here is the idea of the Batcops. I mean, the Batcops idea is at the moment that you are able to build proofs with different degrees. This helps a lot to optimize. I mean, this loss of performance here we are recovering a lot of performance on that side. But even that's still less performant if you count in the cells number. Okay, so this is just a parameter on that. But when you multiply, I mean, the complexity, and here is the degree of the constraints and even the complexity of the full constraints, things starts getting much. And again, when you go to the Windows computation, I think this is much more difficult there. But this is
starting from a simple design. It has advantages.
Yeah, but it's the important here is understanding the best, so the good and the bad of each systems, and you will find. So when you iterate, you will find the right trade-offs.
Okay, cool. Well, and the last topic maybe that is currently also a hot topic is about recursion. I mean, trying to prove things. I mean, try to prove proofs, and then we can enlarge the computation that we are proving, essentially. Okay, so.
Well, with these processors, I mean, when you're having a processor, you have a program, but I mean, the program can be the number of lines of code that you can execute is limited, okay? But the idea here is with recursion, or sometimes we call it with continuation in the case of the processors, but the idea is at the end is just taking many chunks and somehow aggregating them in the building a tree of a proof. And with this, the most interesting part here is that you can build a proof that can be as big as you want. I mean, you just pay more. You just aggregate more proofs and then you can grow much faster. Okay, and this is a big difference when you started with Circle, with that you have the limited number of gates that you can build on that. This is one thing, but there is even more important things. I mean, you can mix with recursion. You can mix proofs, very different proofs. I mean, you can. Generate a proof that, okay, this is a proof that's either this or this, and then you can aggregate to proof. So recursion is, I would say, that's probably the biggest hidden revolution of the zk. People talk about the revolution of zk, but not about that. So the real revolution probably is this recursion, because this recursion enables a lot of things. One of the things that enables, for example, this recursion is the zk rollups. I mean, the privacy. So here, of course, we're talking about the rollup without privacy. Okay? But if you want to build privacy, you need a proof that's actually created in the user's device. Okay? And then you need to aggregate this proof in another proof. That's the rollup part. I mean, and you cannot mix them together. So one is there are two different kinds of proof. but you can prove from one proof you can prove the other. I mean, with recursion you can embed one of the other. And this recursion, I would say, it's useful for many things, but especially for privacy, or for including privacy in the rollups. At least is one of the pieces that's it's super important, fundamental, and I would say not widely exploited yet.
Yeah, I think this idea of being able of mixing different kind of proofs, this is very revolutionary, because I think the very first ones were Coda, I believe, that they were trying to build a succinct blockchain. So the idea was, okay, let's make a proof that the first block is computed correctly, a proof that the second block is okay, and then in the second block the proof would also prove that the previous one was correct. So it was actually for scaling, so that you could verify the latest state with verifying one single proof. And they were only looking at pairing-based snarks. So I think that this idea of, okay, what if a snark verifies a stark, and all of this like opens up a wide variety of possibilities.
Recursion with elliptic curve is not impossible, but it's hard. Okay? It's difficult because you need to work with this chain of curves. It's not an easy part, but here, for example, with Starks, recursion is very, very natural. I mean, it's very easy and very fast. I mean, and this is not the only one, but this is one of the reasons why Starks are getting a lot of traction in current days. There's many reasons. Okay? The other reason is mainly that the primitive, so the basic operation, on a Stark is just a hash, and the basic operation of an elliptic curve is very much a multiscalar multiplication. And also Starks allows you to work with the smaller numbers, so it has a lot of advantages there. And Starks in today's day are faster with the current hardware. I mean, maybe tomorrow somebody invents ISIC that do a multiscalar multiplication super fast, then things change. But at this point, hashing is much faster than multiscalar multiplication, and this is what makes the difference of the performance. The capacity of working with lower prime fields is another differentiation, and the recursion is the other topic. That's why, at this point, I would say that Starks is currently, I mean, at least with the current information, Starks is much superior to that. I mean, there is some interesting work in the elliptic curve about the folding schemas and about these things that somehow are trying to substitute recursion and trying to do that more efficient.
At the constraint level.
Yeah, but I mean, I'm here, of course, I'm in a moment of wait and see and see what they come up, but I'm very skeptical. I'm very skeptical at this point.
In fact, Marta had a result in a crypto that is impossible to generate pairing-friendly cycles.
Yeah, no, well, not exactly impossible, but yeah. So we explored like this maybe unpopular idea of having, well, it's essentially something called cycles of course that would allow to do recursion on pairing-based snarks. So at the end, you only have one pairing. Well, the most complex operation you have to do is verifying a pairing, and this is constant. So regardless of the size of the circuit. So the idea was, what if we can verify one proof of this type with another one? And for that, you needed like these cycles of curves, and there was only one cycle that was known, and then we were looking for more, and we didn't find any, and then we got the results saying like, well, with the technology and the tools we have right now, we're not going to find any cycles. So I think we have got like a lot of negative results in this area. Yeah, exactly. So this is why there are like these half cycles or chains of curves, and so yeah, I see your point.
Elliptic curve proving systems, I would say that the point where are unbeatable right now is in the proof sites. If you really need proof sites and even verification cost, which is in general used to be quite related one to the other, then elliptic curve is elliptic curve. I mean here, Plonk, which is again a variant of Plonk, or even Growth 16. I mean they are still valid proving systems for when you need a proof, okay, I need a short proof and fast to verify, or fast to verify, or cheap to verify on chain, and then you need to go there. Okay, so here the technique that most of the people is using right now is, okay, they are working with the StarX. I mean, they are doing all the operation, all the recursion, all the fast.
And the last step is
the last step is just, okay, verifying the start with a snark, so you have the best of both proving systems.
Yeah.
But again, I mean, this is technology is evolving, and there are some
definitely.
surprises at some point.
Okay, well, as a summary, I would say that we have a lot of theoretical stuff going on, a lot of research in building these systems. We have also this other line of the hardware to accelerate all these things, and let's see where we end. I think